Welcome back class. So last time we were actually learned about the sampling and we derived some relationship here which and in frequency domain. So basically the sampled signal, it can be represented as x of j omega, okay, where omega is basically the discrete time angular frequency, okay. So basically it was just the periodic version of the your sample signal, okay, with factor of 1/2t, okay. So we learned about the aliasing concept, and one very important thing which we learned last time was the relationship between the continuous time and discrete time angular frequencies, okay. So basically omega, the continuous time frequency is discrete time frequency multiplied with the sampled time, okay. So that is the relationship between them. So we can represent them in frequency domain. If we want to talk about the discrete time signal, so we can represent using the continuous time frequency and the discrete time frequency with this relationship, okay. And there was the mathematical expression for those. And then we learned about the sampling frequencies and what should be the appropriate sampling frequencies for the reconstruction of the input signal, okay. And we determined that basically the sampling frequency must be 2 times of the input signal frequency, right. That was the minimum sampling frequency, okay, which must be required for the reconstruction of the input signal, okay. We solved a couple of examples. Okay, now let's see the next thing. Okay, the Nyquist theorem, which is this is basically the theorem which defines that what should be the minimum sampling frequency so that no aliasing should occur. Okay, or in other words, what should be the minimum sampling frequency that you can reconstruct, you can recover your original input signal. Okay, for example, if this is our input signal, okay, and in frequency domain, okay, and the cutoff frequencies, okay, are omega n and minus omega n, okay. And in this like if you talk about in discrete time, okay, so basically in discrete time notation we can represent this as a continuous time with the sampled version, okay, the sampled of the continuous time signal, okay. And basically ts is coming from the sampling frequency, which is actually 2 pi our ts, and ts basically is equal to 2 pi our sampling frequency, okay. So we can replace this ts with this and we can get this one. And here we determined last time also basically that the sampling frequency should be 2 times of the input signal frequencies, okay. So input signal is basically a band limited, okay. Band limited means this signal is existing in this interval from minus omega n to plus omega n, okay. This is the existing interval, and if we go beyond this, okay, for any value which is greater than omega n or greater than minus omega n, this signal is basically 0, okay. So in mathematical form this signal is 0 for any value of the frequency which is greater than omega n or minus omega n. So for this signal sampling, as per the Nyquist sampling theorem, the sampling frequency should be 2 times of this omega n. For example, if this omega n is 4 radian per second, right, so then the sampling frequency, the minimum sampling frequency should be 2 times of this, okay, minimum, that will be 8 radian per second, okay. Or in other words, if you want to get the sampling time, so ts basically will be equal to 2 pi over this, okay. So thus we can calculate the this like the sampling period, the sampling frequencies, or whatever we want, okay. So this is called Nyquist theorem, okay. Omega n is basically called as Nyquist frequency, and the sampling frequency must be 2 times of the Nyquist frequencies, okay. So that in this case there will be no aliasing, that is the minimum criteria. Now let's see the different cases, okay. We have seen this, but we are revising this in a different way now. So we have a band limited input signal, okay, which has a magnitude a, and it is existing from minus omega n to plus omega n, okay. And if we get it's we are doing sampling of this in frequency domain, okay, and we know that in frequency domain we will get this signal, okay. So we are assuming that TS is very small, okay, TS is very small, that sampling time is very small, okay. So sampling time is very small, so sampling frequency will be large, okay, or omega s will be large. So omega s will be large, we will get this output response. So here basically what is happening here, we know that this is 2 pi, so this is like omega n, so this is 2 pi minus omega n, right, okay, time ts, right, because this is in omega domain, so omega is basically discrete times t, okay. So basically in this case we have this God band here, okay. Why? Because our sampling frequency was greater than 2 times of omega n, okay. So if we just simplify this, 2 pi minus omega n into ts is basically greater than this one, omega n time ts, right. So if we just redo this, finally we can get this, that omega s is basically greater than 2 times of omega n, okay. That is the, so this case when the sampling frequency is basically greater than 2 times of omega n, greater than, okay, so basically we will have the space between the samples. So in this case we can easily reconstruct our original signal. So this is our original signal. So if we apply a low pass filter here, okay, if we apply a low pass filter here, that can easily filter out this input signal and we will get our original signal, okay. So this condition is basically called oversampled. If sampling frequency is greater than 2 times of omega n, this condition is called oversampled, okay. Oversampled means you are taking more samples and you have enough space between them, okay. And if your sampling frequency is exactly 2 times of omega n, exactly, okay, in that case basically this spacing will be gone, okay. So we are getting exactly samples at here. So this is called critically sampled, okay. Sampling is going okay, okay, but now, okay, you might face difficulties in reconstruction, okay, in getting of your original signal if you are like your original signal is not becoming zero, okay. For example, if the original signal is going like this, okay, like here you are getting like this, so you might lose some frequency component at this end, okay, because of the critical sampled, okay. Sampling is okay, but this is called critically sampled, the minimum sampling, okay. This is the minimum, okay. Your sampling is okay, okay, 2 times, okay, but that will be the critical sampled. In this case you might lose some component, some frequency characteristics, some frequency components of your input signal, okay, while we are doing the reconstruction. And if it is less than, that is called undersampled, okay. If your sampling frequency is less than, so we know that basically you get one and you are getting the other one here, okay, like this one, and this is the other one. So basically because of their interaction you will get this thing here, okay, this thing here. So this dotted basically representing their overlapping region, okay, this is overlapped region. So in this case if we apply a low pass filter here, so we will get this signal which is not actually our original signal, okay, because here we are having the change of the spectrum, shape of the spectrum. So this is called undersampling condition. So in this case aliasing will happen, okay, you will not be able to reconstruct, okay. So if the signal is not strictly band limited, sampling can still be done at twice the effective band limited, okay. So like omega n, so you should go at least greater than 2 of omega n, okay, at least greater than, so that there should be no aliasing. No aliasing means you can easily get your original signal. And for the reconstruction, so we have learned that, so basically here in this we can apply a low pass filter, and that low pass filter will filtered out this frequency components, which is basically our original signal. So now let's have a look at more details about basically what is happening inside here. So basically you get a discrete time signal, okay, which is this one in frequency domain, okay, this one, okay, in frequency domain, because you take the DTFT of that and you get this signal, okay. and you apply a low pass filter here. Okay, now for the reconstruction, basically what is happening, so first of all we get a discrete time signal, then we convert from the sequence to the impulse train. So basically we take the sample, we apply the sampling on that, we get a sample signal, and then we apply the reconstruction filter. Okay, so basically then we use this filter. Okay, and the minimum, okay, the minimum criteria is that your sampling frequency, okay, and the filter critical frequency should have this relationship. Okay, so we are applying a filter which have a critical frequency of this one minus omega c. Okay, so this critical frequency should be half of the sampling frequency. This is the basic minimum criteria. Okay, what does this mean? This means is that if you want to avoid aliasing, if you want to avoid undersampling, okay, if you want to avoid the losing of the original signal information, then your critical your low pass filter critical frequency should be at least half of the sampling frequency. Okay, and what is our sampling frequency? 2 pi over t. It means critical frequency, it will be 2 pi over t divided by 2. So 2 will be cancelled out. So critical frequency will be pi over t, which is like this one. Okay, and this is basically the analysis in frequency domain. So basically frequency domain analysis is easier for the from the understanding perspectives. Okay, but what is actually happening in time domain? So let's have a look on that. So this is a rectangular signal in frequency domain, right? So if you take its inverse Fourier transform, so if we have a rectangular in frequency domain, in time domain we will get a sinc function which will look like this one with a time period of t. Okay, with a time period of t. Okay, so in time domain basically what is happening, you get a sampled signal, okay, and here you have this impulse sinc function, okay, and they are actually convolving in time domain. Okay, this sampled signal, this is basically convolving with this sinc function. Okay, and once they are convolved, then we are getting actually recovered signal, which is basically will be our actual reconstructed original signal. Okay, so how this happened, okay, with the mathematical formulas, we will see that with the help of examples in the live session. Okay, thank you very much for your time.